The weight is mg, and there's a normal reaction from the table. The weight is mg, and there's a tension in the line. The weight is mg. There's a normal reaction from the surface of the ice. There are no other forces acting on the puck. It's optional to mark in the velocity. The weight is mg. There's a normal reaction from the surface. Normal in this context means perpendicular. Now, if those were the only forces, it would obviously slip down the plane. But it's a rough table, so there's friction. Friction acts so as to oppose motion. It opposes the natural motion which would be down the plane. The weight is mg. There's a normal reaction from the pavement. There's a tension in the lead. We're not told that the surface is smooth, so we should assume it's rough and therefore put in a friction which would oppose the motion. Since it's being dragged to the right, the friction would act to the left to oppose the motion. Those are all the forces. But the dog is being dragged along from rest. Therefore, it's accelerating, and that needs to go into the diagram too, or else it's wrong. It's optional to put the velocity in. Here's one way of showing the forces. There's a weight of mg, a normal reaction from the floor. The mop head is pushing the head of the mop, and it's at an angle of 30 degrees to the horizontal. Quite often we use the letter S for a thrust, and the friction must oppose the motion. If there were no other forces, it would be moving from left to right, so the friction must be this way. Now those are all the forces, that's not wrong, but it wouldn't be considered a good or helpful diagram because we've got a mixture of pushing and pulling forces. Let's have another go. The weight, the normal reaction, the friction, all as before, but it would be better to show the thrust, the force from the handle of the mop, as a pulling force. Even though it's really a pushing force, we show it as a pulling force. Makes no difference, but it makes the diagram more usable. Those are all the forces. It's moving to constant speed, so no acceleration. There's velocity. It would be optional to put that in. Before we put the forces in, let's think about the geometry of the setup. Assuming that the washing line is attached at 2 points at equal height, would this situation be possible where the two parts of the line are at different angles and different lengths? Well, under some circumstances it would be possible, but here the key word is smooth. Because the hanger is smooth, it will slip along the washing line until it's hanging from the centre and the whole situation is symmetrical. Now we understand why the situation is symmetrical, it's easy to put in the forces. The weight is mg, and the tensions in the two parts of the line must be equal because of the symmetry. One subtlety, what we've actually drawn here is the forces on the hanger.